So far we have seen that computing or calculation of any problem is all about doing algorithm and small steps, easy steps. Now, how to implement these simple operations? We need to implement simple operations to repeat, like we did last time in the case of addition and rest of the problems we have seen. Any system we are designing, it has certain design goals. For example, if you design a car, it should run, it should have a steering, it should have tires. A lot of such design goals are there for any system. So like that, this calculation or the system to automate this calculation also has some design goals. So some of the design goals are pretty obvious. So we have seen this small operation we are repeating multiple times. So it should be able to process millions of those operations in a repeated way. And it should not consume much energy. The energy consumption per operation should be very small. Another related design goal is there should not be any friction or any mechanical friction, in fact. The problem is if per operation there is friction or any mechanical movements, it will easily get exponentially high when the number of operations is increased. So no friction, no moving parts, very fast. It should be very fast because these operations we're going to do repetitive. So we're going to do hundreds and thousands of times. It has to be very fast. And it should not generate any heat, which is related to no moving parts and friction. But in case of electricity, heat generates in certain other ways as well. And the list goes on. So these are some of the very strict design goals for this system which we need to design to calculate something. No moving parts. That itself rules out a lot of things in the world, which we know of, all the machines we see has moving parts. This mic I'm using right now, it has a moving part. It has a condenser inside which moves. Then this camera I'm using, it has also moving parts. So lot of the machines we know has moving parts. So no moving parts is a very, very strict guideline. So what we're going to do is we're going to try to implement such a system which doesn't have any moving parts and is also able to do a calculation like the one we saw in the last couple of slides. Any questions? All right. Before we get into the core of the subject, we need to get familiarity with a certain type of numbers called binary numbers. So there are a couple of slides coming up. Before we get into the slides, we'll take the slides as a review. We will get some familiarity with the numbering system which we normally use in our daily life. And then we compare and contrast the binary numbers on top of it. We'll do it in the whiteboard. And then we will come back to the slides. Okay? All right. So let's consider a normal number, 3568. So this is a number which we normally use in our daily life. These numbers are called 10-based numerals. We don't realize that they are 10-based numerals, but they are 10-based numerals. So where this 10 is coming from? So basically this number is, this 3568 is 8, 6, 5, 3 into 10, 10, 10, 10, 0, 1, 2, 3, plus, plus, plus. So this is how this number is calculated. The absolute value of the number is getting calculated. 3 into 10 to the power 3 plus 5 into 10 to the power 2 plus 6 into 10 to the power 1 and 8 into 10 to the power 0, which is 8 into 1 plus 6 into 10 plus 5 into
100.
Yeah, 100 plus 3 into
1000.
That's correct. If you add up all this thing, you will get 3568. Yes. So this is called a 10-based numeral because this is called a base. This This part is called base. So apparently we use 10 base numerals, and most of us are familiar with only 10 base numerals because we use that in daily life, and probably this is one of the oldest systems we use. Now there are other systems as well. The Roman numerals are other systems. I don't want to discuss it here. We can have 2 base numerals, we can have 8 base numerals, 3, any base numerals we can have. So let's see how 2 base numerals works. Before that, I need to highlight on one more property of the base. If the numerals are 10 based, you need to have 10 different characters to represent it. So in our case, we are using 0, 1, 2, 3 till 9. How many characters or how many symbols are there?
10.
10, that's correct. So that is also another feature or another requirement of a 10 based numeral. So if it is 8 based numeral, you can have 8 characters like this, till 7. If it is 8 based numeral, you can have. And if it is 16 based numeral, we'll see a little bit of 16 based numerals as well in our series. How many symbols we need for 16 based numerals? 16, that's correct. So after 9, we will have A, B, C, D, E, and F. So that is the symbols we use for 16 base numerals. The symbols can be anything, any symbols, but you need to have 10 different things to represent it, to show that 10 different values. Now coming to 2 base numerals. So how many symbols 2 base numerals needs? 2, exactly. So normally we represent with 0 and 1. Okay, so any number we can represent using 0 and 1. So let me
Question. Can that be symbols as well?
Yeah, you can use A and B if you want. If you want, you can use A and B. There is no harm in using A and B. This 0 has the value 0 and this has the value 1 as well. So it's easier to represent at 0 and 1 because we are familiar with that convention. You can use A and B if you want and do all the calculations, but the values remain the same. Let me give you a conversion. So conversion will help here to understand a little bit better. So I'm going to write a 2 base numeral, say 0, 1, 1, 0. Okay, so I'm gonna do a similar operation here to convert it into 10 base numeral. Again, 0, 1, 1, 0 into 2 instead of 10. Here it was 10, remember? Instead of 10, I'm going to use 2 here. Into 2, into 2, into 2. Plus, plus, plus. Do you know what's going to come on the power? 0, 1, 2, and 3. Yes, that's correct. So this number, in fact, this 0 is probably optional because any 0, just like the 10 base numeral, any 0 which is coming in front of the number doesn't have any impact on the actual number. Yeah, but rules remain the same. So 0 into 2 raised to 3, which is 0. Yeah, that's right. Yes. Plus, yeah, 1 into 2 raised to 2. Yeah, 4. Yeah, that's right. Plus 2, yeah, 1 into 2 raised to 1 plus 0. Yeah, so this number we will get as 6. 4 plus 2, 6. That's a short intro on 2 based numerals. We'll see in the slides, getting back to the slides, we'll see some more features of these numbers. Why we discuss 2 based numerals is the computing. The modern day computing is completely implemented using 2 based numerals. The song you listen in YouTube, the calculations you do in a computer, the emails you receive, the Facebook page you have, everything is a 2 based number. All the data, everything is a 2 based binary. So why do we learn binary numbers or any other based numerals other than 10 based numerals? In the case of 2 based numerals, it is very easy to build systems which meets the design goals we have seen using 2 based numerals. And that's what we're going to see. Now let's get back to the slides.